Hello and welcome to this lecture of the series Introduction to Algorithms. Today we will be learning about iteration and recursive tree method. As we have already seen that there are basically four ways of solving the recurrences. The first one being the substitution method. The second one is your iteration method. The third one is your recursion tree method. And finally, there is your master theorem method. So we saw how to solve your recurrences using substitution method, where we have to guess. We have to look at the recurrence relation and we have to guess what will be the answer of that. And then we have to use mathematical induction to check if our guess is right or wrong. So as we discussed in that lecture that it becomes oftentimes very much exhaustive for a person to guess the right time complexity of an algorithm, and once you use substitution method it will take time, and if you are not right, so it will be problematic for you to guess again. And at times, as we have seen that the upper limit or the big O notation, it allows us to we can guess a higher upper limit, like we can guess exponential, while it might be having a quadratic or even a cubic time complexity. So we will look at the iteration method first. It's a pretty basic and simple method where we don't have to guess. What we do is that we have to unfold your recurrence. We keep on unfolding it till we find a pattern. And once we find a pattern, we use that pattern to solve that recurrence, and finally we find a result. Okay. So we will take an example or two and see how to go with your iteration method. Okay. So like in previous examples, what I'll be doing is that I'll be giving you a small code snippet of your C language, because that will be easier to understand and comprehend. And then we'll see how a recurrence is derived from that, and we'll solve that recurrence using your iteration method. So the first one is your iteration method. We'll take a small example here. We have taken almost same example in substitution method, or before that when I showed you how to calculate or make recurrences. So here is a simple function. We'll check So what we are doing here is that we are simply displaying your value n, whatever n you enter. As long as it's greater than 0, we'll be displaying it, and we'll be calling same function recursively with the value n minus 1. Okay. So if we calculate the complexity, okay, so this will take 1 unit of time, and this will take time taken by n minus 1. Okay. And the whole algorithm will take time n. Now what we have to do is that we have to simply add it. So I'll be adding it. It will be Tn minus 1 plus 1. So this will happen when n is greater than your 0. And what will happen when n will be equal to 0? It will only be executed once. Okay. So there it is. You have your recurrence. So your recurrence is, it is 1 when n is equal to 0, and it is equal to Tn minus 1 plus 1 when n is greater than 0. Okay. So now what we will do is that we'll use iteration method to solve this recurrence. So we will take this case, that is your T of n is equal to Tn minus 1 plus 1. Okay. So like I said at the beginning that you have to unfold it. So how we can unfold it? We'll unfold this Tn minus 1. We'll use Tn minus 1 and we'll again put it in this formula. Okay. So what will be Tn minus 1 equal to? It will be equal to Tn minus 1 minus 1. Okay, here I am substituting for n, I am using n minus 1. So it will be Tn minus 1 and then this minus 1 and then plus 1. I am expanding this Tn minus 1, okay, and this plus 1 will come outside. Fine. So it will be Tn minus 2 plus 2. Minus 1 is minus 2 and outside it will be 1 plus 1 is your 2. Okay. So now I'll expand this Tn minus 2. So it will be equal to Tn minus 2 minus 1 plus 1 and outside this plus 2 will remain same. Okay. So what will it become? It will become Tn minus 3 plus 3. So you can see now that there is a pattern. So what is the pattern? Pattern is that here it was Tn minus 2 and outside it was plus 2. Here it is Tn minus 3 and outside it is plus 3. So if we go on k times, finally we will reach, it will be Tn minus k plus k. Okay. So we have unfolded it, and after unfolding we have found a pattern, and I'm assuming that after k times it will be n minus k plus k. Now when will this stop? You know that it is a recursive call. It will go on executing till it meets the stopping condition. And what is the stopping condition? When n equal to 0. That is your T0. Here stopping condition is T0. Okay, T0, and that is equal to 1. So I'll assume that this Tn minus k is the stopping condition. It will mean that Tn minus k is actually equal to T0. That's where our algorithm stopped. So if we equate, we see that n minus k is actually equal to 0, which will mean that k is equal to n. Fine. So what we'll do is that we will substitute k equal to n in this equation 1. Fine. So using in equation 1, we'll get Tn is equal to, so Tn minus k is 0. So it will be T0 plus, for this k we can write n. Okay. And you know T0 is 1, so it will be 1 plus n. So this is your time complexity. Now you can see here, your time complexity was dependent on the subproblem. But here it's not dependent on the subproblem, it's just dependent on the length of input. So we can say that it is order of n. Fine. So this is your iteration method, where we take your recurrence, we unfold it till we find a pattern, and then we solve that pattern till we get your final time complexity. So for another example, we'll again first write the code snippet so that we will understand how that recurrence was formed, and then we'll solve that recurrence using your iteration method. So I have another function of same name. Okay. So what we are doing here, instead of looking if n is greater than 0, we are looking at if n is greater than 1. And I'll be telling you why we are looking at n greater than 1. So we'll be checking it if n is greater than 1. And inside we'll have a for loop. For I equal to 0, I less than n, I plus plus. Okay, so inside this for loop, we have a print statement, or any statement we can have. So I am writing this print statement so that we'll get an idea how it is being executed. So after we have printed, what we need to do, we need to have a recursive call to itself. Okay. So what we are having here is that we are having display n by 2 and again display n by 2. So this is just a template, okay? This is just a template. We can have such loops when we are solving some generic problems, like you have your different sorting techniques, merging techniques, or other algorithms. So here is just a template. You should understand how a certain loop or a construct works. Then you can apply same to your algorithm, whatever that will be. So what I'm doing here is that I'm calling again recursively display, but I'm calling n by 2. I'm not calling n minus 2. So that is why I'm checking here n greater than 0. If I'll check n greater than, I'm checking n greater than 1. If I check n greater than 0, what will happen? Is that when it will become 0, so anything divided by 0, that will create a problem. You have seen similar problem when we have traversals in your binary tree. We first go to right hand side and then we go to left hand side. So you can have it twice, you can call same algorithm, okay? So now if we look at the time complexity of this algorithm, when n will be greater than 1, this will be executed n times, okay? And this will be executed t n by 2 times. Same way, this function will be executed t n by 2 times. Fine. So if we see, if we add it up, this is the total time complexity, that is Tn for this algorithm. So if we add it up, it will be twice Tn by 2 plus n. Fine. But when will this happen? This will happen when n is greater than 1. Okay. And what will happen when n will be equal to 1? It will only check this condition once. So it will be when n equal to 1. Fine. So now we have our recurrence. So our recurrence is t of n equals, it is 1 when n equal to 1. Fine. And it is equal to 2t n by 2 plus n when your n is greater than 1. Fine. So you can see that we are learning multiple things here. We are not only learning how to solve your recurrences using iteration method, we are also learning how to calculate your time complexities. Here time complexities are recursive in nature, they are recurrences, but you are also understanding how to calculate your time complexities. So this is our recurrence. I'll be rubbing that portion because we need space to write. So now what we will do is that we'll unfold this recurrence. So we have t of n equals 2t n by 2 plus n. What we'll do is that we'll open this t n by 2, okay? So it will be equal to 2 is outside. So this t n by 2 will substitute for n, will substitute n by 2. So it will be 2t n by 2 multiplied by 2 plus n by 2 plus n. Fine. I have simply opened this t n by 2, which will be equal to t n by 2 multiplied by 2 plus there is n. So for that n we'll be having n by 2 and this n is outside as it was. Okay. So if we open it, it will become this 2 multiplied by this 2 is 4, but we won't be writing 4, we will be writing 2 square. Why we are writing 2 square? Because it will help us to generate a pattern. If we write 4 at that time, it will be difficult to generate a pattern. Although pattern will be there, but it will be difficult to identify that pattern. Okay. So I'm writing 2 multiplied by 2 is 2 square, then t multiplied by this n divided by 2 multiplied by 2, I will again write n square, that is 2 square. Plus I'll write this 2 will be multiplied by this 2, it will get cancelled. It will be only n, okay, and then plus n. Fine. Now what we will do is that we'll again open this n by 2 square, okay. So before opening this n by 2 square, this n plus n will be equal to your 2n. So 2 square t n by 2 square plus this n plus this n is 2n. Fine. Now we'll open this. So it will be equal to 2 square will be outside. So I'll be opening this. It will be t n by 2 square multiplied by 2 plus this n, this will be substituted by n by 2 square. Okay, then plus 2n is outside as it is. Okay, so if we again multiply it, it will be 2 square. We had this 2, we didn't write it here, it is 2t. Okay, when we open this, we have to write the 2 that is in the formula. So 2 multiplied by 2 will be 2 cube. Then it will be t n by, this will be 2 square multiplied by 2 is 2 cube. This is 2 square and this 2 square will get cancelled. There will remain n plus 2n will be 3n. Okay, so we have found a pattern. What is the pattern? The pattern is 2 raised power whatever, that is 3. Then we have to take tn divided by 2 raised power same power, that is 3 here, and we have to plus it 3 times n. Okay, so if we keep on opening it, unfolding it up to k times, what will we get? We will get t of n equal to 2 raised power k t n by 2 raised power k plus kn. Means if we go on opening this thing up to k times, when we go on opening it up to k times, we will get this thing. Okay, so this is what we need to finally solve. I'll name it as equation 1. Fine. So like in previous algorithm, what is the stopping condition here? The stopping condition is n equal to 1. In previous algorithm, it was n equal to 0, but here it is n equal to 1. So the stopping condition, we have n equal to 1. That means T1 is the stopping condition. Okay, that is equal to 1. Which means that your this T n by 2 raised power k, T n by 2 raised power k is actually equal to T1. It is your stopping condition. That's why your algorithm will stop here. Okay. So we can see that your n by 2 raised power k is equal to 1. Fine. Which further means that n equal to 2 raised power k. But we don't need n, we need k. What we'll do, we'll apply log. Once we apply log to both sides, we'll get log of n is equal to log of 2 raised power k. And log a raised power b is b log a. So log of n will be equal to k log 2. So log 2 is 1. It will imply your k is equal to log of n. What we'll do is that we'll use this value in equation 1. Fine. So if we use this value in your equation 1, we'll use two values rather. We'll use this value and this value. So 2 raised power k is equal to n. So finally your Tn will be equal to, for this 2 raised power k, we'll substitute n. Okay. And this Tn, this will be equal to T1. Okay, because this is the stopping condition, plus Kn, plus Kn. So K is your log n multiplied by n. Fine. So if we move further one step, so T1 is 1, so your Tn will be equal to n log n plus n, this n. Okay. So what will be the, here what will we have order? It is order of n log n. The upper limit is your n log n. Fine. So with these two examples, we saw how to use iteration method, which is pretty simple. All you have to do is that you have to unfold your recurrence till you find a pattern. Once you find pattern, you have to solve for the unknown values, that is k, because we only want your answer in n, that is the length of input. So we solve for k in terms of n. We substituted those values back in this equation, and we got your time complexity. We got the upper limit, that is order of n log n. Like I have said before, while introducing these different methods for solving your recurrences, that recursion tree method is nothing, it is just representing your recursion in the form of tree, where each node of your tree represents the sub-problem. Because you know, in a recurrence relation, we are having sub-problems, means we are having recursive calls to the algorithm itself. So in recursion tree method, what we do is that we represent your recurrence relation in terms of a tree, where each node represents a sub-problem. Then we can check or see the time for each sub-problem, and then we can add it up. Once we add it up, we can find the actual time complexity of your algorithm. Now, the thing here is that some people use your recursion tree method just to get an idea or the estimation of the time complexity. Like we saw in your substitution method, where you need to guess the time complexity. What some people do is that they use this recursion tree method quickly to get an idea. They don't get an exact answer, but they get an idea. And that value they use as an guess in the substitution method, and there they prove it, that if it is right or wrong. So in case you are doing that, you can be a little sloppy, and you can skip some details to get an idea of your time complexity, which you can use as a guess in your substitution method. But if you do it properly, what you can do is that you can actually generate your upper bound or lower bound using your recursion tree method. So we will have a look at it with the help of an example. Fine. So what we'll do is that we will see the recurrence that I showed before this one, that is that we use in the iteration method. The recurrence there was T of n was equal to 1 when n was equal to 0, and it was equal to T of n minus 1 plus n when n was greater than 0. Fine. So now what we will do is that we will use your recursion tree to solve this recurrence. Fine. So before going into this, let me give you an idea with the help of a live example. Means we won't go into the this one because this is T, and we'll see a program, a small program, and we'll actually see what will be the output. Okay. So if we have say in the previous example, if we use display 3, okay, we have to display 3. What will happen? Once we'll call display 3, it will display 3 plus it will call display 3 minus 1, that is display 2, it will call. Okay. At 2, it will display your 2, and at the same time, it will call display 2 minus 1, that is 1. Okay. So here it will display your 1, and it will call your display 0. Because display 0, n is equal to 0, so here it will not display anything. Okay. So we can look here that here it took 1 unit of time, here it took 1 unit of time, and here it took 1 unit of time. Okay. Plus it has to call this function, so calling will also take 1 unit of time. So if we add these up, it took how much? 4 units of time. So what was n here? N was 3, because we called display 3. Fine. So for n equal to 3, we got answer 4, that is n plus 1. Fine. So this is actually your recursion tree. Now because here the value was limited, the value was 4, or sorry, the value was 3 here for n. So we could draw the entire recursion tree, and we simply add up the value time taken by each subproblem, and we got the total time. Fine. Now instead of using a value 3, we will be using value n. Okay. And what we'll be doing is that we'll be drawing same tree, but there the values will be in terms of n, not in terms of your constants, that is 1, 2, 3, 4. Fine. So now let's try drawing recursive tree for this problem. Fine. So at the top there will be this is the root node, will be Tn. When we will call Tn, what will happen? When we will be calling Tn, what will happen is that it will print n times. It will print n. whatever the value is there, n, that is 3. Plus it will call t n minus 1. Fine. Next, what will it do? It will here print n minus 1 and it will call t n minus 2. Fine. So what it will do, this will print n minus 2 and it will call t n minus 3. So this will go on up to where? Up to 0. Fine. So it will go on till it becomes your t2. It will print 2 and it will call t1, and finally t1 will print 1 and it will call t0, and t0 will do nothing. Fine. So this and this is same. The only difference is that there we are using only 3 values and here we are using n values. We know that it will first go call for n and it will print simply n. It called for display 3 and simply printed 3 and call 3 minus 1, that was display 2. Here it will call t n minus 1, then it will print that n minus 1 value and call n minus 2. It will go on till it becomes t1, it will print 1 and finally it will call t0 and it won't print anything. Fine. So if we look at the time taken here, what is the time taken here? So here it will be time will be n minus 1. Here it will be n minus 2. Okay. Here it will be n minus 3. Then there will be 2, then there will be finally 1. So what we'll do is that we'll simply add it up. Fine. So we are beginning from here. This one will take n, then n minus 1, then n minus 2, then n minus 3, so on, 2, then 1. Fine. So what will be the time taken here? It will be 1 plus 2 plus 3 plus 4 plus so on up to n minus 3 plus n minus 2 plus n minus 1 plus n. Okay. So is this series familiar to you? What will be the sum of the series? It will be n into n minus 1 divided by 2. So we can write it n into n plus 1 divided by 2. So it will be n square plus n divided by 2. So if we take the upper order, that is big O, it is n square. Fine. So with this example, we saw how to use a recursion tree to solve your recurrence. Fine. So up till now, we have seen 3 methods. In this lecture, we saw iteration and recursion tree method, and in the previous lecture, we saw what we call your substitution method. So in iteration method, what we do is that we take your recurrence, we simply solve your recurrence, we unfold it till we find a pattern. Once we find your pattern, we solve your pattern and we get your time complexity. In recursion tree method, what we do is that we take your recurrence and we represent it in the form of a tree, where each node represents sub-problem. Then we see the time taken for each sub-problem and we simply add it up. Once we add it up, we might need to do little maths here and we will get an equation. From that equation, we'll take the higher order term for your big O. That will be, for in this case, it was order of n square. So this finishes our 3 methods for solving your recurrences. And what we'll be doing is that now we'll be solving some examples with these 2 methods, especially that is iteration and recursion tree method in coming lectures. So I hope that you understood today's lecture and I hope to see you in the next lecture as well. Thank you.